Welcome to the Deep Dive. We're your shortcut to getting smart on complex topics, pulling out the key ideas from important sources. Today we're diving into something that's, well, everywhere in our digital lives. Data-intensive applications. I mean, think about your social media feed, online banking, even just sending a message. It's all underpinned by this massive amount of data that needs storing, processing, delivering reliably.
It really is. These systems are kind of the hidden engines behind almost everything we do online. And understanding them, even just the basics, gives you this really valuable intuition for how modern software actually works. Our source today is Martin Kleppmann's Designing Data-Intensive Applications. It's pretty much the definitive guide.
It really is comprehensive. So our mission here is to pull apart the key ideas, the algorithms, the principles for building systems that are reliable, scalable, and crucially, maintainable. We want to find useful ways to think about why they work the way they do, and maybe even more importantly, figure out what question you should be asking. Develop that gut feeling for what's going on underneath.
Exactly. So let's start with, I guess, the three big challenges, the pillars: reliability, scalability, and maintainability. They're not just buzzwords. They're like the core problems you have to solve.
Okay, reliability first. What are we really talking about when we say a system is reliable?
Reliability at its heart is about the system continuing to work correctly, even when things go wrong. And they will go wrong. We call these things faults. And it's not just, dramatic hardware failures like a disk dying. It's also software bugs, unexpected ones, and maybe surprisingly often, human errors, like someone pushing a bad config.
Right. And one of the scarier things is this idea of cascading failures, isn't it? Where one little hiccup triggers a whole chain reaction. I've even heard some companies, they deliberately cause problems just to test things.
Absolutely. Cascading failures are often kicked off by these dormant bugs, flaws, just sitting there until some weird combination of events happens. And yeah, what's really interesting is how some places tackle this, like Netflix famously with their Simian Army. It's software that deliberately, randomly, shuts down servers or injects latency.
Wow.
The big idea there isn't just, oh, we can break things. It's that by making failure routine, making it expected, you force yourself to build resilience right into the core design. You're not just patching holes. You're building something fundamentally robust.
Embracing the chaos to build stronger systems. That really flips the script on reliability.
Okay, so moving from things breaking to things just getting bigger. Scalability, how do we define that one?
Scalability is basically how well your system copes when the load increases. Growth.
Yeah.
But before you can even talk about coping with growth, you need to describe the current load. What are the key numbers? We call these load parameters.
Load parameters are like what? Things like maybe requests per second to your web server, or the ratio of reads to writes in your database. That mix really matters. Or maybe it's the number of active users, like concurrently connected.
Okay. And when we talk performance under load, people often use latency and response time. Are they the same thing? I feel like they get used interchangeably sometimes.
Yeah, they do, but there's a crucial difference. Latency is really the time our request is waiting, being handled. It's kind of the hidden time, the time it's latent. Response time, though, that's the full round trip from the client's perspective. Sending the request, network delay, maybe time spent in queues, the actual processing time, and the network delay coming back. It's the whole experience.
Gotcha. So response time is what the user actually feels. And it's not just the average time that matters, right? I keep hearing about percentiles. Why are those so important?
Averages can be really misleading. The median, or the 50th percentile, tells you half your requests are faster than that value, which is useful, but the 99th percentile, or the 99.9th, tells you about the worst experiences. The slowest 1% or 0.1% of requests. Those outliers are often your most valuable customers, or at least the ones most likely to complain loudly.
Ah, right. So you need to care about the tail end of the distribution.
Exactly. And those higher percentiles, they often get baked into service level objectives, SLOs, and service level agreements, SLAs, the contracts defining performance. Focusing there forces you to handle those painful edge cases.
That makes a lot of sense for keeping users happy. Speaking of real-world stuff, the book uses that Twitter example for scalability challenges, right? With the tweet fan out.
Oh, yeah, that's a classic. So initially when you tweeted, Twitter would push that tweet out immediately to the timelines of all your followers. Fan out on right. Worked fine for most people, but then, celebrities join, millions of followers.
Right, suddenly you're writing to millions of timelines instantly.
Exactly. It absolutely hammered their right infrastructure, just couldn't scale for those massive accounts, so they shifted. It's now a hybrid approach. For most users, it's still fan out on write, but for those huge accounts, the tweets are actually fetched and merged into your timeline when you load it. Fan out on read, essentially, for the celebs.
Ah, clever. Shifting the load depending on the scale of the user, that really shows the trade-offs.
Mm-hmm.
And when engineers talk about dealing with load, they often mention scaling up versus scaling out. What's the difference there?
Right. So scaling up, or vertical scaling, that's just getting a bigger, beefier machine, more CPU, more RAM, faster disks, one powerful box. Scaling out, or horizontal scaling, is distributing the load across many machines, often smaller, commodity hardware, sometimes called a shared nothing architecture, because each machine is independent.
So one big machine versus lots of smaller ones.
Yeah, kind of. But the reality is good architectures usually mix them. You rarely go purely one way or the other. Maybe you scale out to a cluster of pretty powerful machines, not just one giant one, but not thousands of tiny ones either. It's usually a blend.
Okay. So systems that work when things break, systems that grow. The last pillar, maybe less flashy, but super important, maintainability. What does that cover?
Maintainability is really about making life easier for the humans involved.
Yeah.
The engineers, the operations teams, everyone who has to work with the system over time. It includes things like operability, how easy is it to run the system day to day? Can you monitor its health effectively? Are deployments predictable? Stuff like that. Keeping the knowledge about the system alive, too.
And a big part of that is simplicity, trying to cut down on what's called accidental complexity.
Exactly. Accidental complexity isn't inherent to the problem you're solving for the user. It's the extra complexity that just comes from the implementation choices. Overly convoluted code for simple tasks. Good abstractions are key here. They hide the messy details, let you reuse parts, and just make the whole thing easier to understand and change safely. And finally, there's evolvability. Recognizing that things change, requirements change, new features get added, platforms shift, laws change. Your system has to be designed to adapt without needing a total rewrite every time.
Right. Good abstractions, operability, evolvability, it's about the long game.
Totally.
Okay, foundational principles down. Now, let's dig into where the data actually lives. This feels like a really fundamental choice.
Yeah.
How do you structure your data in the first place, like relational versus document models?
Yeah, it's huge. The relational model, SQL, tables, rows, columns, proposed by Cod back in 1970. It was dominant for, 25, 30 years, which is ancient history in tech.
But then came the birth of NoSQL. Why did these alternatives pop up? What problems were they trying to solve that relational couldn't?
Several things kind of came together. Agile development methods made developers want more flexibility, less rigid schemas that needed slow migrations. The sheer volume of data exploded, especially unstructured stuff. And honestly, it kind of reopened debates from way back in the 70s. Before relational really won out, you had hierarchical models like IBM's IMS used for inventory on the Apollo missions, believe it or not, and network models. Relational wasn't the first database idea.
And one big driver for NoSQL was this thing called the object-relational mismatch, right? What's that about?
Yeah, that's a big one. If you're writing code in an object-oriented language, you work with objects, maybe nested objects, lists inside objects. It's often tree-like. Mapping that rich structure onto flat relational table, sometimes called shredding, can feel really awkward. You end up with lots of tables, complicated joins, maybe an ORM layer trying to hide it all, but it adds complexity.
So if your data naturally look like a document or a tree,
then a document database might be a much more natural fit. They're designed to store that whole structure, that document, together as one unit. If you usually load the whole thing anyway, it can simplify your application code a lot.
Okay, so if I'm starting a project, how do I choose? When is document better? When is relational still the king?
Generally, document models shine when your data is pretty self-contained, tree-structured, and you usually access the whole document. Thing like a user profile, maybe. But if you have lots of complex relationships, many-to-one, many-to-many connections that you need to query across frequently, the relational model, with its powerful join capabilities and strong consistency guarantees, is usually still the better bet. Document databases often struggle with joins.
And what about schema? Document databases are often called schemaless. That sounds nice and easy, is it?
Well, schemaless is a bit of a misnomer. It's more like schema on read. The database doesn't enforce a structure when you write the data. You can put pretty much anything in there. The structure is implicit, and it's up to the application reading the data to interpret it.
Versus relational, which has a strict, enforced schema defined upfront.
Right. Schema on write. The trade-off is flexibility versus potential chaos. Schema on read gives you flexibility, but if different parts of your app start writing slightly different structures, the reading code gets complicated fast. Relational schemas are rigid, which can feel constraining. But most modern databases make alter table pretty fast now, though, yeah, some older versions, like MySQL historically, could lock up the whole table for ages while copying data. It's a trade-off. Rigidity versus potential runtime messiness.
Okay. Data models covered. How do we actually ask questions? Query languages. There's this split, imperative versus declarative. Can you break that down?
Sure, imperative is telling the computer how to do something step by step. Like if you're using JavaScript to find something in a web page, you might write a loop, check each element. You're giving explicit instructions. Declarative is describing what you want, not how to get it. SQL is a classic example. You say select name from users where country UK. You don't tell it how to find those users, whether to scan the table, use an index.
And that's where the query optimizer comes in, right? That's the magic of declarative.
That's the huge advantage. The database's query optimizer figures out the best execution plan. It looks at available indexes, data statistics, and decides the most efficient way. And this abstraction is powerful because you can add a new index later, and the optimizer might just start using it automatically, speeding up your queries without you changing a single line of application code. You specified the what, the system optimizes the how.
Very cool. Okay. What if my data isn't neat tables or documents, but it's all connected, like a social network or road maps?
Then you're probably looking at graph-like data models. These are really the most natural way to represent highly interconnected data. Think nodes or vertices representing things, and edges representing the relationships between them.
Like people and friendships, or cities and roads.
Exactly. They give you huge flexibility. You can model all sorts of different relationships easily, and adding new kinds of relationships or nodes later is often much simpler than restructuring relational tables.
So if you wanted to ask, like, find all my friends' friends who live in London, a graph database would be ideal, using languages like Cypher or SparkQL.
Spot on. Those languages are designed to traverse these relationships efficiently. Doing that kind of multi-hop query in SQL can get really messy with lots of self-joins. Graph databases make it feel natural.
All right, fascinating stuff on models. Now let's get into the engine room. Storage and retrieval. Even if I'm not building a database, why should I care about the internals?
Because understanding, even roughly, how different storage engines work helps you choose the right one for your application's specific needs, and it helps you tune it better. Is your app mostly reads, mostly writes? Big updates, small reads, different engines optimized for different workloads.
Makes sense. So let's look at a couple of key approaches. First, log-structured storage. LSM trees are often mentioned here. What's the basic idea?
The core concept is surprisingly simple. All writes just get appended to the end of a file, like writing entries in a diary or a log, sequentially. To find things quickly, you keep an index in memory, usually a hash map, that maps keys to the byte offset in the log file where the latest value for that key is stored. Simple, right? Databases like Bitcask and React use this.
But that log file just grows and grows.
Yeah.
And you get old values cluttering it up.
Right. So in the background, the system runs compaction and segment merging processes. It rewrites parts of the log, throwing away duplicate or overwritten values, keeping only the latest version of each key, and reclaiming disk space. The really key insight with log-structured approaches, especially LSM trees, which are a bit more complex than the basic log, is that they offer fantastic write performance. Why? Because appending sequentially to a file is super fast, especially in SSDs, much faster than random writes.
Okay, sequential writes are fast. Now, contrast that with B trees. The book calls them the standard index implementation in almost all relational databases. Been around forever.
Yeah, B trees are everywhere since the 70s. They work very differently. Instead of appending, they organize data into fixed-size blocks or pages, typically 4 KB or larger. When you update data, they usually overwrite the value in place within its page. They maintain a balanced tree structure, so finding any piece of data takes a predictable, usually small, number of disk reads, proportional to the logarithm of the number of keys. They're optimized for reads and updates in place.
So, LSM trees, great for writes. B trees may be more balanced or better for reads.
Generally, yes. LSM trees tend to have higher write throughput and often better compression because sequential data compresses well. B trees can sometimes suffer from fragmentation, wasted space within pages, and write amplification, where one small change might require rewriting a whole page. But B trees offer more predictable read latency. It's a trade-off.
And besides these primary indexes, databases often have secondary indexes, right? Like indexing a user ID column.
Exactly. You often need to look up data by something other than its primary key. A secondary index lets you do that efficiently. For instance, find all orders placed by a specific user. Since these values aren't necessarily unique, the index usually stores a list of matching primary keys or row locations. And then you get into more specialized stuff like full text search for finding words within text documents, or fuzzy indexes using things like Lucene, which can find words even with typos searching within a certain edit distance.
Okay, this leads nicely into optimizing for different kinds of work. There's this big split, OLTP versus OL. Can you explain that?
Yeah, online transaction processing, OLTP, versus online analytic processing, OLAP. Fundamentally different workloads. OLTP systems are what typically back your main applications. They handle lots of concurrent short transactions, reading or writing a small amount of data, responding quickly. Think booking a flight, making a bank transfer, posting a comment. Interactive stuff. OLAP is about analytics, business intelligence, running complex queries over huge volumes of historical data to find trends, generate reports. Think, what were our total sales by region for the last quarter? These queries scan millions of rows, do big aggregations, not interactive in the same way.
And because the workloads are so different, usually have separate systems. That's where data warehouses come in.
Precisely. Trying to run heavy analytic queries on your live OLTP database can kill its performance for regular users. So you typically extract data from your OLTP systems periodically, transform it, and load it into a separate data warehouse optimized purely for OLAP queries. These data warehouses often still use a relational model, usually with specific schema designs like star schemas or snowflake schemas. These involve a central fact table with your core events or measurements linked out to dimension tables that describe the context, customers, products, dates, locations, etc.
And inside these data warehouses, there's this really cool optimization, column-oriented storage. This sounds like a big deal for analytics. How does it work?
It's a fundamentally different way to lay out data on disk. Instead of storing row after row, like ID1, name 1, city 1, ID2, name 2, city 2,
Yeah.
you store all the values for one column together, then all values for the next column, and so on. ID1, ID2, ID3, then name 1, name 2, name 3, then city 1, city 2, city 3.
Ah, so if your analytic query only needs, say, the sales amount and region columns to calculate totals?
Exactly. You only need to read those specific columns from disk. You skip reading all the other columns, like customer name, product description, etc., that aren't needed for that query. For wide tables with many columns, but queries that only touch a few, this massively reduces the amount of data you need to pull from disk. It's a huge win for OLAP.
And I bet that helps with compression, too. Columns probably have repeating values.
Absolutely. Columns, especially dimension columns like country or product category, often have lots of repetition. This makes them highly compressible using techniques like bitmap encoding or run length encoding. Better compression means more data fits in memory, faster scans. Combine that with something called vectorized processing, where the CPU can operate on chunks of this compressed columnar data very efficiently in tight loops, and you get enormous speedups for analytic queries.
Wow. And to make things even faster, you can pre-calculate results with materialized aggregates.
Right. These are things like materialized views or data cubes. If you know users frequently ask for, say, total sales by month, you can pre-compute those totals and store them. When the query comes in, the database just reads the pre-computed result instead of scanning the raw fact table. It makes common analytic queries incredibly fast.
Okay, we've seen how data is stored and queried. Now, let's venture into the wild world of distributed systems. The book really shifts tone here. It's like, okay, now things get really hard.
Yeah, it's a definite shift. The fundamental assumption changes. On a single machine, things are relatively predictable. In a distributed system connecting multiple machines over a network, you have to embrace pessimism. Assume anything that can go wrong will go wrong, eventually.
And the prime suspect is the network itself. Unreliable networks. What kind of gremlins live in the network?
Oh, all sorts. Packets get lost, they arrive out of order, they might even get duplicated, and maybe worst of all, they can be arbitrarily delayed for seemingly no reason. Then you have network partitions, where some part of your network just gets cut off from the rest. Maybe a switch fails or someone unplugs the wrong cable. The nodes might be perfectly healthy, but they just can't talk to each other.
And figuring out why you can't reach another node is tricky.
Extremely. Did the other node crash, or is the network just really slow right now? Or is there a partition? Most systems rely on timeouts. But if you set the timeout too short, you might wrongly declare a node dead when it's just slow, too long, and you wait ages before reacting to a real failure. There's often no perfect value.
And network congestion, just too much traffic, is a big cause of those delays.
It's a primary cause, especially in shared environments like data centers or the public internet. Switches get overloaded, packets queue up, just like traffic jams on a highway. It introduces unpredictable delays. The core takeaway is assume the network is unreliable and delays can be unbounded. You have to design your system to tolerate that uncertainty.
Okay, unreliable networks. What's next on the list of things we can't trust? Clocks.
Right. Computer clocks are not as simple as you might think. There's a key distinction. Time of day clocks versus monotonic clocks.
Oh,
Time of day clocks are what tell you it's, 3.42 p.m. They try to sync with real-world time using protocols like NTP, but they can jump forwards or backwards due to sync adjustments, leap seconds. They're not perfectly smooth. Monotonic clocks just measure elapsed time like a stopwatch. They always go forward. They're good for measuring durations on a single machine, like timeouts, but they don't tell you the actual time, and different machines' monotonic clocks aren't related.
and relying on time-of-day clocks across machines can lead to weird stuff, like causality violations.
Totally weird stuff. Because of clock skew's slight differences in clock speeds or NTP adjustments, you can have node A send a message at time 100 meters, according to its clock, and node B receive it at time 99 meters, according to its clock.
Whoa, looks like the message arrived before it was sent.
Exactly. It breaks our intuitive sense of cause and effect. If you rely on timestamps for ordering events, like in a last write wins scenario where you just keep the write with the latest timestamp, clock skew can mean you keep the wrong version, potentially losing data because the later write happened on a machine with a slightly slower clock.
So if physical clocks are unreliable for ordering across machines, what's the alternative? You mentioned logical clocks earlier.
Right. Logical clocks like Lamport timestamps are a safer way to capture causality. They don't care about real time. They just assign incrementing counters to events based on the happens before relationship. If event A could have caused event B, e.g. A sent a message that B received, then A's timestamp must be less than B's. It preserves the logical order, which is often what actually matters.
Unreliable networks, unreliable clocks. What else can pause or delay things, processes themselves?
Absolutely. Your application process isn't guaranteed to be running constantly. It can pause for surprisingly long periods. Garbage collection pauses in languages like Java or Go can sometimes freeze an application for seconds. The operating system might just decide to preempt your process to run something else, context switching. If you're in a virtual machine, the hypervisor might pause your entire VM, steal time. These pauses can wreak havoc with response time percentiles and make coordinating distributed actions even harder. A node might miss heartbeats or hold locks for too long simply because it was paused unexpectedly.
All this uncertainty, network delays, clock issues, process pauses, leads to a pretty stark conclusion in the book, right?
Huh.
About knowledge and truth.
Yeah, the core consequences. A node in a distributed system cannot know anything for sure. It only has its local view, based on messages it has received, or perhaps messages it hasn't received, like missing a heartbeat. It can only make educated guesses about the state of other nodes or the network. Is that node down? Or just partitioned? Can't be 100% certain. And acting on wrong guesses can lead to big problems.
Like having two nodes think they are the leader at the same time.
The classic split brain scenario, which is where techniques like fencing tokens come in.
Fencing tokens, how do they help?
Okay, imagine a node. Node A thinks it's the leader and holds a lock on some resource, maybe shared storage. It experiences a long GC pause. While it's paused, the system declares it dead and elects a new leader, Node B. Node B gets the lock. Now Node A wakes up, it still thinks it's the leader and holds the lock. It might try to write to the shared resource, potentially corrupting data written by the actual current leader, Node B.
Is that?
Right. A fencing token prevents this. When the lock service grants the lock, it also gives the node a unique, monotonically increasing token, like a version number for the lock. Every write request to the shared resource must include the token. If the old leader, Node A, wakes up and tries to write using its old, stale token, the storage service sees that a higher token has already been used by Node B and rejects Node A's write. It fences off the old leader. It's sometimes brutally called stoneth, shoot the other node in the head, prevent zombies.
Stoneth. Wow, okay, that's clever. So we've painted a picture of a chaotic world, but we do build systems that work on top of this. How do we handle data duplication, replication, and keep things coordinated?
Replication is fundamental. You want multiple copies of your data for fault tolerance and sometimes for performance, reading from nearby replicas. But the instant you have multiple copies, you have the problem. How do you keep them all consistent? If I write to one copy, how and when does that write get to the others?
And the most common way is leader-based replication, right?
Right.
Master-slave.
Yep. Also called primary replica now sometimes. It's the most common setup. All writes must go through a single designated node, the leader. The leader processes the write, updates its local storage, and then sends the data change out to all its followers, the replicas. Reads can often go to the leader or any follower, depending on consistency needs.
And there's a key choice here in how the leader sends changes. Synchronous versus asynchronous replication.
Right. Synchronous means the leader waits for confirmation from at least one, or sometimes all followers, that they received the write before acknowledging success back to the client.
That sounds safer, more durable.
It is more durable. If the leader crashes right after confirming, you know the data is safe on at least one follower. But it makes writes much slower because you're waiting for that round trip to the follower. Asynchronous means the leader sends the change but doesn't wait for confirmation. It acknowledges the client immediately, much faster writes. But if the leader crashes before the change reaches any followers, that write might be lost. Most systems default to asynchronous for performance, accepting that small risk of data loss on leader failure.
And this delay between the leader getting it right and followers getting it, replication lag, can cause weird issues for users, right? Like read your writes.
Definitely. Read your writes consistency means if a user makes a change, like updating their profile, and then immediately views their profile, they should see the change they just made. But if their read request goes to a follower that hasn't received the update yet due to lag, they might see the old data, which is confusing, but I just saved it.
Yeah, that'd be annoying.
Yeah. Other related issues are monotonic reads, meaning you never see time go backwards, like seeing a counter decrease after you saw it increase, and consistent prefix reads, ensuring you see sequences of causally related writes in the correct order. Handling lag is surprisingly complex.
Okay, leader-based is common. What about alternatives? Multi-leader replication.
Multi-leader means you have, well, multiple nodes that can accept writes, often used in multi-data center setups, where you want a leader in each location to reduce write latency for local users or for applications that need offline capability.
Sounds good, but I sense a catch.
The huge catch is write conflicts. What happens if two users write to the same data concurrently, but through different leaders? Which write wins? You need mechanisms for detecting these conflicts, often asynchronously after the fact, and crucially, logic for resolving them.
Maybe
Last write wins, but problematic with clock skew. Maybe merging values. Maybe you need application-specific logic. Maybe complex structures like version vectors. Conflict resolution is the Achilles heel of multi-leader.
Okay, so multi-leader has conflict issues. What about no leader at all? Leaderless replication.
Like Dynamo.
Right, the Dynamo style, used in systems like Cassandra and React. Here, writes don't go to a single leader. They get sent directly to several replicas. Consistency often relies on quorums. To write, you need acknowledgments from W replicas. To read, you query R replicas. As long as W plus R is greater than N, the total number of replicas, your read quorum is guaranteed to overlap with your write quorum by at least one node. So you should get an up-to-date value.
Should.
Oh yeah. Quorums provide some guarantees, but things can still get out of sync. So these systems also use background processes. Read repair, where a client notices inconsistencies during a read and pushes the latest version to stale replicas. And anti-entropy processes that constantly compare replicas and fix differences. They also often use things like version vectors to detect concurrent writes that happen without seeing each other. This helps identify siblings conflicting versions of the same data, which then often require the client application to merge or choose between them. This feels like it's leading towards the CKP theorem. Consistency, availability, partition tolerance. Pick two. What's the expert take on CAP these days?
CAP. It's famous, maybe too famous. The idea is simple. In a distributed system facing a network partition, you have to choose between maintaining consistency, C typically meaning linearizability, or availability, A, every request gets a response, even if potentially stale. The expert view now is, well, CAP is a bit simplistic and often misunderstood. You don't just pick two, like ordering pizza toppings. Network partitions happen. So the real choice is always, during a partition, do you sacrifice consistency or availability? And the C in CAP is very specific, linearizability, while real systems often use weaker, more practical consistency models. So while historically important, it's often best avoided as a primary design tool today. There are more precise ways to talk about these trade-offs now.
Okay, avoiding CAP. But let's talk about that strong C linearizability. What exactly does that guarantee? And when do you really need it?
Linearizability is the strongest single-object consistency model. Makes the system appear as if there's only one single copy of the data, and all operations on it happen atomically, instantaneously, in some well-defined global order that's consistent with the real time the operations occurred. It's like everything happens in a single orderly queue.
So it makes the distributed system behave like a non-distributed one for that piece of data.
Pretty much, yeah. You need it for things where you absolutely cannot tolerate ambiguity or stale reads. Think implementing unique constraints, like usernames, distributed locks, or leader election. You need definitive agreement. Single leader replication can potentially provide it, though it's tricky. Multi-leader and leaderless systems generally cannot guarantee linearizability, especially across data centers due to network delays. And remember, even RAM on your CPU isn't linearizable without special instructions. It's expensive to achieve.
It really hammers home how complex this is. Okay, so linearizability is about a total order, but sometimes a partial order, like causal consistency, is enough.
Yes. Often, we don't need everything to be in a single global timeline. We just need to preserve causality that happens before a relationship. If event A caused event B, we need to ensure everyone sees A before B. Causal consistency provides this without the strict ordering requirements and performance cost of linearizability. Lamport timestamps, which we mentioned earlier, are a way to track this causal order.
And this relates to consensus, right? Getting everyone to agree.
Exactly. Consensus is the fundamental problem of getting multiple nodes to agree on something, like who is the leader or did this transaction commit, reliably, even if some nodes crash or messages are lost. Algorithms like Paxos and more recently Raft are designed to solve consensus. They provide strong guarantees. All nodes that decide on the same value. You can't decide twice. If a value is decided, it was proposed by someone. And eventually, if enough nodes are working, a value will be decided. They usually involve leader election and quorum-based voting.
And there's a deep connection between consensus and linearizability.
A profound one. It turns out that solving consensus is equivalent to implementing linearizable compare and set registers, and also equivalent to implementing total order broadcast, where all nodes deliver the same messages in the same order. If you have a reliable algorithm for any one of these, you can use it to build the others. They are, in a sense, the same fundamental problem.
Wow, okay. And systems like Zookeeper provide these consensus-based building blocks.
Precisely. Zookeeper implements consensus using its own protocol called ZAB, similar to Paxos, to provide things like linearizable atomic operations, total order broadcast, distributed locks, group membership, leader election, these crucial primitives that other, more complex distributed systems can then build upon.
Okay, deep breath. We've gone through the guts of storage, replication, consistency, consensus. Now let's look towards the future, or at least how complex systems are actually built today. Integration and correctness. The book argues no single tool fits all, right?
That's a key takeaway. Real-world complex applications rarely rely on just one database or one type of data store. You'll inevitably end up combining multiple specialized tools. Maybe a relational database for transactional data, a document store for user profiles, a search index like Elasticsearch, a cache like Redis, an analytics warehouse.
Which sounds powerful, but also potentially messy.
Yeah.
How do you keep data consistent across all these different systems?
That's the huge challenge of data integration. If you try to do dual writes, writing the same piece of information to, say, your database and your search index simultaneously in your application code, you're asking for trouble. What if one write succeeds and the other fails? They get out of sync.
Yeah, I can see that happening easily.
A much more robust approach is often to funnel all the primary writes through one system of record, typically your main database. Then, use mechanisms to reliably propagate changes from that system to all the others that need derived versions of the data. Think of it like establishing a single source of truth and deriving everything else from it.
Which brings us to derived data and the data flow model. What's derived data?
Derived data is essentially data that's computed or reformatted from your primary source of truth. It might be redundant, but it's often essential for performance or specific access patterns. A search index is derived data. A cache is derived data. A materialized view is derived data. Keeping it up to date involves capturing changes from the source. Techniques like change data capture, CDC, where you tap into the database's internal replication log, are becoming really popular. Or event sourcing, where you architect your application around storing an immutable log of all state-changing events as the primary record.
So instead of mutable state, you have an immutable log.
Right. The log becomes the source of truth. You can replay it to reconstruct current state or feed it into different processors to build various derived views, search indexes, caches, analytic summaries. It makes systems more auditable, easier to debug, and allows for evolving views over time without changing the core event log.
And this ties into unifying batch and stream processing. We used to have separate systems, the Lambda architecture.
Yeah, Lambda architecture had separate paths. A batch layer for processing all historical data periodically, and a speed layer for handling real-time updates, merging the results at query time. It worked, but it was complex. Two code bases, tricky merges. The trend now is towards unified systems, often built around stream processing concepts. Use a stream processor that can handle both live data and replay historical events from a durable log, like Kafka or Pulsar. You write your processing logic once, and it works for both historical reprocessing and real-time updates.
It's like building an index. You process the existing data, then just keep applying the new changes as they stream in.
That's a great analogy. You bootstrap by processing the history, then just keep consuming the live feed. And if you zoom out, you can start to see the entire data flow across an organization as one huge database. The event logs are the core data, the stream processors are like triggers or materialized view refreshers, and the various databases, caches, and indexes are different kinds of indexes optimized for specific queries.
Wow. Unbundling the database into specialized communicating components.
Exactly, like the Unix philosophy. Small tools, doing one thing well, connected by pipes, or in this case, event streams. The pattern is often database inside out, composing specialized storage and processing tools using application code, often relying on asynchronous event logs with idempotent rights for communication rather than expensive distributed transactions.
Okay, this sounds powerful, but also relies heavily on things working correctly, which brings us to aiming for correctness. How do we achieve exactly once processing in this stream world? If a processor crashes and restarts, won't it process messages twice?
Exactly once is the holy grail, though often it's more accurately, effectively once. The key is usually a combination of idempotent operations and transactionally updating both the processed result and the offset in the input stream. Idempotency means doing the operation multiple times has the same effect as doing it once. A simple way is using unique IDs for events or requests. If your processing step involves writing to a database, you can include the event's unique ID and have a uniqueness constraint in the database. If the processor restarts and tries to process the same event again, the database write fails because the ID is already there, effectively once.
Ah, okay, so the database helps enforce the once part, even with retries.
Right, but standard database transactions often don't work well across different systems, like writing to a database and sending a message. That's where things get trickier.
And sometimes maybe perfect consistency isn't needed. The book mentions compensating transactions.
Yeah, this acknowledges that in the real world, especially in business processes, sometimes it's okay to have temporary inconsistencies if you have a reliable way to fix them later. A compensating transaction is an action that undoes the effect of a previous transaction. Think like booking a flight and hotel might involve separate steps. If the hotel booking fails after the flight is confirmed, you don't roll back the flight, which might be impossible or expensive. Instead, you execute a compensating transaction, cancel the flight booking. It's an application-level way of handling failures in multi-step processes, sometimes called the saga pattern. It's about designing for recovery and apologies.
Makes sense for business logic. And finally, the book reminds us that even hardware isn't perfect. Data corruption happens.
It's rare, but yes. Bit flips in RAM or on disk due to cosmic rays, hardware bugs like rowhammer. Subtle corruption can occur. It's unavoidable at scale. So you can't just assume data, once written, is perfect forever. You need auditing and integrity checking, periodically verifying data, checking checksums, maybe even rerunning derivations from source data to see if you get the same result. Systems like blockchains use cryptographic hashing extensively to make tampering immediately obvious. It's about detection and repair, accepting a degree of inherent imperfection.
Wow, what a tour. From the basics of reliability and keeping things running, through scaling to handle massive load, the different ways data can be modeled and stored, the sheer nightmare fuel of distributed systems, and finally, how we try to integrate everything and aim for correctness.
It's a lot, for sure. But hopefully you now have a better intuition for the challenges involved, the trade-offs being made constantly under the hood. Understanding why things are complex helps you make better choices, ask better questions, and appreciate the engineering that goes into the systems we rely on every day.
Absolutely. And as we wrap up this deep dive, thinking about Kleppmann's work and the incredible power of these data systems leads to a final thought. We spend so much time figuring out how to build these complex, powerful systems. But maybe the deeper question we need to keep asking ourselves is, for whom are we building them, and to what end? As engineers and creators, how do we ensure the immense power of data is wielded responsibly, ethically, and ultimately in service of building a better, more humane world? Something to reflect on.